Hi, and welcome to the fifth and final video for section 10.3. In this video, we're going to look at some special cases. So when we do these systems of linear equations, we have three possibilities for solutions. First off, maybe there's no solution. So there's no values of x and y and z if it's a three-variable system. If it's a two-variable x and y, maybe there's no values that we can pick that'll make this system true. So when that happens, what we get is, in our reduced row echelon form, we get a row of zeros equal to some constant c. And this implies no solution. And again, we'll look at some examples here, so we'll point back to this, what we're talking about. The second possibility is one unique solution. And this is what we saw in the previous videos, video 3, video 4. We had that system, three equations, three variables, and we ended up with -3, 1, and -2. So that was the only solution that would work, and that's when we get each row begins with a leading a leading variable. So each row begins with a leading variable. So if we're doing reduced row echelon form, as we did in video 4, we're just going to get ones on every single diagonal. We're not going to have 0 at one of those diagonal points. We're going to have a 1 along there, and that's if we're reducing it to 1. We could obviously have, as we did earlier, where we might have 2x equals 4, so we divide both by 2, but we're essentially having just one value in each row corresponds to one constant value. And lastly, an infinite number of solutions. And this is a row of all zeros. So the first one was all zeros, but we had some number in the last column. In this case, every single value is a 0, which means we have an infinite number of solutions. So let's look at a couple examples. Let's say we have x minus 3y plus 2z is 12. 2x minus 5y plus 5z equals 14. And x minus 2y plus 3z is equal to 20. So if I set up this matrix, I get what? 1, -3, 2, 12, 2, -5, 5, 14, 1, -2, 3, 20. So I have a 1 in this position. That's good. I'll leave it. So let's get zeros in these positions here. So I'm going to do row 1 times -2 plus row 2 gives me a new row 2. So if I rewrite row 1, I get 1, -3, 2, 12. So now multiply this by -2. -2 plus 2 is 0. 6 minus 5 is 1. 2 times -2, -4 plus 1 is 5, plus 5 is 1. And -24 plus 14 is -10. Now how about this one down here? So I need to do row 1 times -1 plus row 3 gives me a new row 3. So if I do -1 times that, add it 0. 3 minus 2 is 1. -2 plus 3 is 1. -12 plus 20 is 8. So now I want to get a 0 down here. Get a 0 at this triangle. I'm working towards reduced row echelon form, ideally. So I'm going to do what? I'm going to do row 2 times -1 plus row 3 gives me a new row 3. So I leave row 1, 1, -3, 2, 12. Leave row 2, 0, 1, 1, -10. And now multiply row 2 by negative 1 and add it. So 0 times negative 1, 0 plus 0 is 0. Negative 1 times 1, negative 1 plus 1 is 0. Negative 1 times negative 1 is negative 1 plus 1 is 0. Negative 1 times negative 10 is positive 10 plus 8 is 18. So this is our sign. We have an issue. We have a special case. And it's what? It would be case number 1, no solution. So I have all zeros and then a constant value in the final column. So what this tells me is I can't pick any values for x, y, and z that will make all 3 of these equations true at the same time. Let's look at one more example. So again, then on this one it'd be no solution. I can't pick any values that would make it true. All right, how about this example? We have negative 3x minus 5y plus 36z equals 10. Negative x plus 7z is equal to 5. And x plus y minus 10z equals negative 4. So, I'm going to put this in matrix form to begin. Now remember what our elementary row operations are. We can switch rows, right? So even though it's written this way, it's arbitrary what order I write this. So if I was to put this into the matrix as it's set up, I'd have what? Negative 3, negative 5, 36, 10. But this last row, I ideally want a 1 in this position here, right? And so if I use this last row first, it's going to give me a 1 in that position. So I'm just going to switch these 2 rows when I write it into the matrix. You could write the whole matrix and then switch them and rewrite it again, but it's just kind of doing double work. So I'm going to write this row first, 1, 1, negative 10, negative 4. Leave the second one alone, negative 1, 0, 7, 5. Don't forget there's a 0 there, a placeholder. And then the last one, negative 3, negative 5, 36, 10. So now, I want to get a 0 here, so I'm doing what? Just basically multiply this row by positive 1 and add it to it. So I have row 1 times 1 plus row 2 gives me a new row 2. So essentially I'm just adding the 2 rows, right? So 1 minus 1, oh, let me rewrite this, sorry. 1, negative 1, 1, 1, negative 10, negative 4. So 1 minus 1, 0. 1 plus 0, 1. Negative 10 plus 7, negative 3. Negative 4 plus 5 is 1. Now what do I need here? I need to do row 1 times positive 3 plus row 3 gives me a new row 3. So I'll multiply this by 3. 3 times 1 is 3 minus 3, 0. 3 minus 5, negative 2. Negative 30 plus 36 is positive 6. And 3 times negative 4 is negative 12. Plus 10 is negative 2. So now I want to get a 0 down here where this negative 2 is. So I leave row 1 and row 2 alone. So I have what? 1, 1, negative 10, negative 4. 0, 1, negative 3, 1. So I have to do what? I have to multiply this row by 2. So I'm doing row 2 times positive 2 plus row 3 gives me a new row 3. So when I do that, 0 plus 0, 0. 2 times 1 is 2, plus minus 2 is 0. 2 times negative 3, negative 6, plus 6 is 0. 2 times 1 is 2, minus 2 is 0. So we have all zeros on the bottom row. So that tells us what? It tells us we have an infinite number of solutions. So now what we're going to do, if you remember quite a few videos back, when we had an infinite number of solutions, we said let x equal x, and then we plugged that back into the system and said y is equal to some equation in x, in the variable x. Well, in this case, what we're going to do is we're going to use a fourth variable. We're going to use t. So I'm going to say let z equals t, because as we saw in that other example, even though we have an infinite number of solutions, it doesn't mean we can just pick any numbers we want. We need to be particular with our selection. So we're going to say let z equal some variable t. Now we can use back substitution. So in this second equation we have what? So from equation 2 we get y minus 3z equals 1. So if z is equal to t, this means y minus 3t equals 1. So add 3t to both sides. Y is equal to 1 plus 3t, or 3t plus 1, depending on how you write it, but either way is okay. So now I have z, now I have y, I can back substitute that into equation 1, and I get what? X plus y minus 10z equals negative 4. So substitute what I had, so I have x plus y, which is 1 plus 3t, minus 10 times z, which is t, equals negative 4. So we get what? X plus 1, 3t minus 10t is minus 7t, equals negative 4. Subtract 1, x minus 7t equals negative 5. And now add 7t to both sides. It says that x is equal to 7t minus 5. So my solution set is going to be the value for x, which is 7t minus 5. Y, which is 3t plus 1. And z is equal to t. So if I pick a value for t, let's say 0, then that means y is 3 times 0, which is 0 plus 1 is 1. And x would be 0 minus 5, negative 5. So this is one possible solution. Negative 5, 1, 0. If you plug that in here, all of these are going to be equal. Or what if t equals 1? Well, then y is 3 times 1 is 3 plus 1 is 4. How about this one? 7 minus 5, 2. So 2, 4, 1 is also a solution that if I plugged it into each of those equations would come out true. So that's how we handle the infinite solutions. We saw no solution in the previous example. And I know it was a lot of time, but that finally wraps up the videos for section 10.3.